Welcome to Cookie's Maths and Science Hub. Today, we'll continue to explore radiation through the lens of nuclear decay equations. Before we get into these equations, let's have a quick refresher on radiation and the main types we're exploring. If you need more details, make sure to check out our short video on the radiation types. So, in a nuclear decay reaction, also called radioactive decay, an unstable nucleus emits radiation and is transformed into the nucleus of one or more other elements. That is, an unstable parent nucleus decays into a stable daughter nucleus plus some radioactive particle or radioactive energy. Our three main types are alpha, beta, and gamma. An alpha particle, given the symbol alpha, is composed of 2 protons and 2 neutrons, and so it is the same as a helium nucleus. A beta particle, given the letter beta in the Greek alphabet, is an electron ejected from the nucleus, not from the shells of electrons about the nucleus. Again, the process of that is far more complicated than we'll be covering in these videos for the time being. And finally, gamma rays, given the symbol gamma in the Greek alphabet, are energy traveling as waves or photons emitted from unstable nuclei. So, recall that a balanced chemical equation reflects the fact that during a chemical reaction, the bonds within atoms and molecules break and reform, and atoms are rearranged, but the total number of atoms of each element are conserved and do not change. That is, whatever's on the left-hand side, or the reactants, must be on the right-hand side, or the products. If you need a bit more information on this, I suggest you check out our chemical equation video. Now, a balanced nuclear equation, on the other hand, doesn't deal with atoms. It actually deals with the subatomic particles. That is, our neutrons, protons, and electrons. So a balanced nuclear reaction equation indicates there is a rearrangement during a nuclear reaction, but of subatomic particles rather than of atoms. So that means whatever protons and neutrons are on the left-hand side must be on the right-hand side. And you can see that in our nuclear equation on the right here. We must have the same number of protons and mass on each side, but the elements themselves can change. So whilst our X on the left-hand side, or our number of protons and neutrons together, has to be equal to the number of protons and neutrons on the right-hand side. So as touched on there, our nuclear reactions must follow the same conservation laws as our standard chemical reactions, in that whatever is on the left must be on the right. And they are balanced in 2 distinct ways. The sum of the mass numbers of the reactants equals the sum of the mass numbers of the products. Now remembering our isotopic symbols, the top number, in these cases on the right here, the X, F, and H are our mass numbers, whereas the bottom numbers, Y, G, and Z, are the charge numbers. And the sum of the charges of the reactants also must equal the sum of the charges of the products. So if on the left-hand side we have X, and on the right-hand side we have FH for our mass numbers, that means X must be equal to F plus H. For our charge numbers, our Y on the left-hand side must be equal to G plus Z on the right-hand side. Now remembering, those charge numbers 90% of the time will represent just our proton numbers. And in most of these basic nuclear equations, when we're not dealing with lots of different charges, that's all they'll be handling. So we can say they're the same number of protons on each side, and the mass number is the protons and neutrons together. Let's start looking at some examples now. Let's look at an alpha decay example first. So uranium-238 undergoes alpha decay, and we're told we need to write the nuclear equation. First, we know our reactant, given the question, is uranium-238. So we can write this out using its isotopic symbol, which is 238-92U. Remembering the letter is simply the letter given to that element on the periodic table. The number at the bottom is the number of protons, which again you can get from the periodic table. And our mass number is given to us in the question, 238. So, given that, we also know that one product will be an alpha particle. Now this is very important. If something is undergoing decay, that means it's giving off that particle. So when we say alpha decay, it means that alpha particle is going to be on the right-hand side, or a product of this reaction. And we represent our alpha particle as our 4,2 helium, as that is a helium atom. As we've said, alpha is the same as a helium, or we can use the alpha symbol, but still giving it the same mass and charge, because it is the same. 4 protons and neutrons together, and 2 protons. As such, we have so far, we know our uranium-238, which is 238-92 uranium, gives us some element, we're not sure what that element is, plus 4,2 helium, because that is our alpha particle. Using our conservation laws, we know we need to have 92 on the right-hand side in our charge numbers. So our Y plus 2 must equal 92. So in this case, we know our Y must equal 90, And our x has to equal, when added to 4, 238. So we know our x must equal 234. And you can see there we've got that balance. So we've got 238 equals x plus 4, or in this case, 234 plus 4, and that equals. Whereas our y, 92 equals y plus 2, therefore our y must equal 90. Now, knowing our y equals 90 gives us our proton number, or our atomic number, which we can use to discover that this element is thorium, or Th, on the periodic table. Rewriting that equation out now, we have 23892U, or 238 uranium, gives us 23490 Th, or 234 thorium, plus our alpha particle, 42 helium. And that is a balanced nuclear equation. Using that exact same process again, let's look at a beta decay example now. Carbon-14 undergoes beta decay, and we're told we need to write the nuclear equation. So first, we know our reactant is 14,6 carbon from the mass of carbon and its atomic number on the periodic table. Again, that charge number is usually the proton number. It can change when dealing with isotopes, but for these examples, we're only looking at the base atoms. We also have one product that we know, which will be a beta particle. Remembering a beta particle is simply an electron ejected, so we can simply write it out as 0, -1, and in this case the charge is important because it's not a proton we're dealing with. Remembering the charge on an electron is -1, or we can write it out as 0, -1 with the beta symbol. But you'll usually see it as the E representing the electron. Now there's some other parts that go into beta decay, such as positrons and other elements, but we're only going to just focus on the very basics in this video. As such, we have so far, writing out our equation, 14,6 carbon gives us some element plus our electron, so 0, -1 E. Given this, looking at what we have, we know that 6 must equal y take 1. So y must equal 7. Now in this case, it can be a bit odd because the y is actually greater than what's on the left-hand side, but remember our electron is -1. Now our x is easy because the electron has no mass, therefore the mass of our new daughter nucleus must be the same as our parent nucleus, meaning that it's as simple as x must equal 14. Given our periodic table with y equals 7, we must now know that A must be nitrogen because nitrogen has an atomic number of 7 on the periodic table. Writing that out, we have 14,6C, which gives us 14,7N plus 0, -1 E, or carbon 14 gives nitrogen 14 plus an electron. A slightly different example now, we're going to deal with a bombardment question. So, in this example, boron 10 is bombarded by a neutron. This leads to alpha decay of the particle. Write the nuclear decay equation. When something is bombarded, whether by a neutron, an alpha particle, or electrons, beta particles, we must be careful because that means that bombardment is on the left-hand side as it is initial reactant, rather than the decay, which is on the right-hand side. So, in this example, we know our reactant is 10,5 boron, from our mass of boron given in the question, and boron's place on the periodic table being 5 from its atomic number. We also know it reacts with a single neutron. Remembering the mass of a neutron is 1, and it has a neutral charge or 0 charge. So we can represent that as 1, 0, n. Similar to how we represented our electron, we only have the 1 in the mass spot for this one, and it has 0 charge. We use a lowercase n to avoid confusion with nitrogen and any other elements that use the letter n. Same again, we know we have one product, which will be an alpha particle, because our alpha particle is what's decaying in this, our boron 10 is decaying via alpha decay, so it's going to produce that alpha particle. As such, we have so far, writing out our equation, 10,5 boron plus our neutron, so 1, 0, n, gives us some unknown element plus our alpha particle, 4, 2 helium. Using this, we need to be careful here because the numbers on the left have to equal the numbers on the right, but that means we need to include the numbers of what is bombarding our initial atom. So in this case, we have 10 plus 1, so our mass on the left-hand side is going to be 11, which means our mass on the right-hand side must be 11 as well. And on the bottom, we have 5 plus 0, so our charge on the left-hand side, or our number of protons, is 5, and the charge on the right-hand side, or the number of protons, will also have to be 5. This means our y value must be 3, to give us 3 plus 2 equal to 5, and our x value must equal 7, to give us 7 plus 4 equal to 11. Given that our y value is 3, A must be beryllium, or Be. Writing this equation now fully out, we have 10, 5b, or boron 10, plus a neutron, 10n, gives us beryllium 7, 7 for beryllium, or Be, plus 4 2 helium, or that alpha particle. Just being careful when you read these questions is pretty much the easiest way to make sure you're getting them right. They're not that confusing with their maths, but just making sure you realize what's on the left-hand side, whether it's being bombarded or added to that initial atom, and what's on the right-hand side when it's decaying into those products or if something's being added afterwards. So just being careful with those, and you'll be able to hopefully work through these problems and balance them out quite easily. Thanks for watching. Hopefully now you have a good idea of how to use these nuclear equations with alpha, beta, and gamma decay, as well as a few bombardment situations. Be sure to like this video and leave a comment for future topics you want to see explored. Please make sure to subscribe to the channel for all future content, and we hope to see you back again soon.